Have you ever crushed a salt crystal and noticed how it shatters like glass but never melts in your hand like wax? That's the first sign you're dealing with something ionic. Let's explore how the nature and structure of a compound tells us what type of bond holds it together. Electrovalent or ionic compounds are formed when a metal donates electrons to a nonmetal, creating oppositely charged ions that attract each other strongly. Think of sodium and chlorine. Sodium loses one electron to become Na plus and chlorine gains one to become Cl minus. In contrast, covalent compounds arise when two nonmetals share electrons. Take hydrogen gas for example. Two hydrogen atoms share one electron pair to form a stable H bond. Now, physical state plays a big role too. Ionic compounds usually appear as hard crystalline solids. Their rigid lattice structures are a result of strong electrostatic forces. On the other hand, covalent compounds can be found in all three states: solid, liquid, or gas, depending on the size of the molecule and the nature of molecular forces. What about attraction? Ionic compounds boast powerful forces of attraction, electrostatic pull between ions. Covalent compounds? Their forces are weaker, van der Waals or dipole-dipole interactions between molecules. So, salt is a solid because of ionic bonding. But why is carbon dioxide a gas? Because it's held together by weak intermolecular forces. Quite the contrast, isn't it? Now here's a fun experiment. Hold a piece of camphor in your palm. It slowly disappears. That's volatility in action, a signature trait of covalent compounds. Let's talk volatility and how thermal stability varies in ionic and covalent compounds. Ionic compounds are non-volatile. Their strong ionic bonds require a large amount of heat to even budge. Covalent compounds, with their weak molecular forces, tend to be volatile. They vaporize easily. This also reflects in melting and boiling points. Electrovalent compounds like sodium chloride have very high melting points, over 800 degrees Celsius, due to the strength of ionic bonds. Meanwhile, covalent compounds like iodine melt and boil at much lower temperatures since breaking molecular forces requires far less energy. So, the next time you see naphthalene balls disappear from your closet or smell perfume evaporate from your skin, you're witnessing covalent volatility in action. In short, ionic equals thermally stable but stubborn to melt, covalent equals delicate and quick to vaporize. Imagine this: you place a metal spoon in hot tea and it burns your fingers. Now place plastic and it doesn't. What's at play here? Heat conductivity, and chemistry has its own version. Electrovalent compounds, especially when molten, conduct both heat and electricity very well. Why? Because in the molten state, ions are free to move, they transport heat and carry electric charge. But in the solid state, ions are locked in lattice positions and can't move, so they don't conduct electricity. Covalent compounds, on the other hand, don't conduct electricity in any state, solid, liquid, or gas, since they lack free ions or charged particles. Let's take a closer look. Solid sodium chloride, non-conductor. But molten sodium chloride, excellent conductor. Meanwhile, glucose, a covalent compound, remains a non-conductor in both solid and aqueous states. So, if you're running current through a compound in the lab, ask yourself, is it ionic and molten? Only then, expect the diameter to jump. Have you ever seen water bubbling during electrolysis? That's science and electricity working together, and ionic compounds make it all possible. Electrolysis is the chemical breakdown of a compound using electricity. Ionic compounds like sodium chloride can be electrolyzed in molten or aqueous states. Here's what happens. In molten sodium chloride, Na plus ions move towards the cathode, C ions migrate towards the anode. They're attracted by opposite charges, and this movement forms the basis of electrolysis. Let's spell it out. Sodium chloride solid, when melted, becomes sodium ions plus chloride ions. NaCl gives N plus Cl minus in molten state. This ionic dissociation is what allows electrolysis to occur. In contrast, covalent compounds like ethanol or glucose do not dissociate into ions, so they cannot be electrolyzed in normal states. However, some polar covalent compounds like hydrogen chloride can react with water to form ions, which makes electrolysis possible in special cases. Bottom line, electrolysis loves free ions, and ionic compounds deliver them brilliantly. Voiceover script. Here's a challenge. Try dissolving chalk in water. Doesn't work. Now try salt. Instant solution. That's solubility in action, and it all depends on the type of bonding. Ionic compounds like sodium chloride are soluble in water, a polar solvent, because water molecules surround and separate the ions, allowing them to dissolve. Water has a high dielectric constant, meaning it weakens the electrostatic attraction between the ions. Covalent compounds, especially nonpolar ones like benzene or naphthalene, prefer to dissolve in nonpolar organic solvents like hexane or ether. This is summarized by the famous chemistry rule, like dissolves like. So NaCl dissolves in water, not benzene. Benzene dissolves naphthalene, not NaCl. This property helps us in real life too. From drug design to cleaning agents, choosing the right solvent depends on the compound's nature. Let's now compare how these compounds behave during reactions. Ever seen a white precipitate form instantly when two clear solutions mix? That's an ionic reaction, and they happen fast. Ionic compounds react through ion exchange, as ions are already present and just rearrange. Their reactions are usually instantaneous and occur in aqueous medium. For example, mixing silver nitrate and sodium chloride gives silver chloride, a white precipitate, in seconds. In contrast, covalent compounds undergo slow, molecular reactions. Bond breaking and bond formation must occur, requiring energy and time. Think of esterification, when acetic acid reacts with ethanol in the presence of acid to form an ester and water. It takes time and heating, a signature of covalent reactions. So, ionic is equal to fast and flashy, covalent is equal to slow and steady. Let's now understand ionization, the ability to form ions in solution. This is what gives compounds their power to conduct and react. Electrovalent compounds like sodium chloride ionize easily in molten or aqueous state. They separate into Na plus and Cl minus ions and conduct electricity. Covalent compounds generally don't ionize, but there are exceptions. Hydrogen chloride is one. In gaseous form, it's covalent and neutral. But when dissolved in water, it reacts to form ions. HCl plus H2O gives H3O plus plus Cl minus, that is, hydronium ion and chloride ion. This ability depends on polarity. Polar covalent molecules can undergo ionization in specific solvents like water. So ionic compounds are born ionized. Covalent compounds need just the right partner, like water, to do it. So, let's recap what we've discovered about chemical bonding and properties. Ionic or electrovalent compounds are born from electron transfer between metals and nonmetals. They form hard crystalline solids, are non-volatile, melt at high temperatures, conduct electricity in molten state, and dissolve in water. Covalent compounds, built from shared electrons, exist as molecules. They can be gases, liquids, or soft solids, are usually volatile, melt and boil at lower temperatures, do not conduct electricity, and prefer organic solvents. From salt in your kitchen to perfume in your room, the behavior of substances can often be traced back to the type of bond they possess. I hope this session helped you see how bonding determines the very nature of a compound, whether it conducts electricity, dissolves in water, or even holds its shape. In the next video, we'll discuss the summary chart structure of electrovalent and covalent compounds. It's going to give you a clear visual breakdown of how these compounds are structured and how their properties align with their bonding nature. Catch you in the next class with more bonding brilliance. Until then, keep exploring chemistry all around you.